Hello, everybody. It's still a pleasure to be participating and giving a talk in this workshop of this program, even though we're resorting to Zoom and virtual lectures. I'd be happy to answer any questions as we go through the talk. So I'd like, for those of you who were also at the tutorial sessions a few weeks ago, there'll be some of the topics that I spoke about in that tutorial. I'm going to spend a little more time and go into some detail here in a few of those topics that I wasn't able to cover in as much detail during the tutorial, as it was more of a tutorial about Hamilton-Jacobi computation using level set methods. Okay, so let's go ahead, and the outline for the talk is one of first an overview, so recapping the reachability methods for hybrid systems and how we use Hamilton-Jacobi methods for that. So we'll recap what a reachable set is and its computation, and illustrate it through a couple of examples. And then for the very last part of the talk, as I did in the tutorial, I'm going to spend a few minutes talking about integrating machine learning into these methodologies in order to develop systems for robotics which are reactive, which include dynamic and real-time sensing about things that are happening online and eventually about the environment. So the first part of the talk focuses more on an introduction and then the issues about computation, very relevant for high-dimensional Hamilton-Jacobi, and the latter part of the talk focuses on how one might incorporate data-driven methods in real time into these Hamilton-Jacobi methods. Okay, so let's start with a recap, and we're going to introduce this concept called a backwards reachable set. Okay, so a reachable set is quite an intuitive concept, I believe, and I've illustrated it here in this sort of stylistic picture, where if you had a control system, a differential equation with a state x in Rn, in this case on the slide it looks like R2, a control input U, and U is a signal that is in general in Rm, and a disturbance D here, which is, sorry, just getting used to my cursor, a disturbance D, which is in RP. So again, control and disturbances, which are assumed to be bounded. So the interpretation here is that there's some system dynamics. There's a control input which you as the designer have access to and you have the ability to influence. And then there's some disturbance D which you as the designer don't have access to. You don't have the ability to manipulate it. But both the control and the disturbance are assumed to be bounded. And we can, depending on what type of problem we want to solve, we can assume different bounds. For this talk, I'm going to assume that we have worst case bounds on each of those. So for the control input, that it limits the ability of the controller to, issue a bound beyond a certain range. Similarly for the disturbance. So while you as the controller wouldn't know what the disturbance is going to do or how it's going to act at any given point in time, you do know the bounds on that disturbance, which can help. So then in terms of what this backwards reachable set is, so this, given the initial data, which is described here as this set G at time 0, and it's a set, it's pictured in this stylistic diagram as an ellipse, and it represents some set, for example, a set of states that you don't want the system to get into. So I've colored it red for sort of danger states. The backwards reachable set is all states over a time horizon t, so this set G of t, is all states for which, for all possible control actions, there's a disturbance action that could push the system into this set G at time 0 in at most t time units. All right, so the interpretation here is that we're working over a time horizon which ends at time 0. So t, it's going backwards. So t is some time before time 0. And we're computing that set backwards in time, or we're trying to characterize and then compute this set backwards in time. So in this case, this is some state x, for which at time t, it's characterized as unsafe, because even for the best possible control input, there's a disturbance action which over that time horizon from t to 0 could result in a trajectory of x dot is equal to f of x ut, which ends up in g at 0 in t time units. Now, the control, this problem of having the ability to control in the face of disturbance, which may be, you don't know what it's going to do, it's a disturbance, but it could be acting against you, led us to formulate this problem of computing a reachable set as a game problem. So in which the disturbance is attempting to do its worst to force the system into an unsafe region, this region G at time 0, and the control is doing its best to try to keep the system in a region which is outside of that set G of 0. So just sort of a little bit more interpretation here. This pink region represents the backwards reachable set. This pink region and the red region, so the union of that represents the backwards reachable set. The blue region is everything outside, and the boundary is everything outside. So if you're in the blue region, that means that, given the definition of this backwards reachable set, that there exists a control which can keep you outside of this set G of 0 for at least t time units. And that's important for control problems, robotics problems. Okay, so that's the setup of the problem we're looking at, and what we did was to show that the computation of that backwards reachable set G of t can be performed by first characterizing that set G of t as the sub-zero level sets of a function j, we'll call it j of xt, which represents a value or a cost. In this case, we're looking at the unsafe regions as being region where j is less than 0. So we could think of this as a value. So as j gets higher, the function, the situation becomes more and more safe. And that function j can be computed by solving this particular form of a Hamilton-Jacobi Isaacs equation. Isaacs because it's got this game problem in it, where the control is trying to do its best to keep the system out of this unsafe region for at most t time units, and the disturbance is trying to do its worst to get the system into that region. And it's doing that through this max-min operation over an inner product between the dynamics of the system and the outward pointing normal of the function j of x at time t. So suppose, for example, at time t0, we're operating on the boundary of this region. So we look at a state that's right at that point. Here's that outward pointing normal, dj dx. And so if the dynamics we're pushing, if for a given control and disturbance, the dynamics, the vector field we're pointing in this direction, that would mean that the dot product between those two vectors is negative, which would mean that when you look at the right-hand side of this equation, the right-hand side would just capture that max min, and the function j would change over time. If on the other hand, that dot product were positive, then the computation would freeze. And in that way, the propagation only encompasses those states for which those states for which there exists a trajectory which could get into that set G of 0 in the time horizon given. So the effect of that min with 0 is to basically freeze trajectories once they enter that unsafe region. You don't want them to leave that unsafe region and then be characterized as safe later in the time horizon. Okay, so this is a mathematical characterization of that, and we worked on this several years ago, and then Ian Mitchell in his PhD thesis characterized that and proved this. And there have been a number of other people in the community of control and dynamic games working on different formulations of this. In particular, more recent formulations with Margellos, Zidani, Mo Chen, who's going to come later or present a talk later in the week, and Jaime Fizak, who've looked at more efficient formulations of this for time-varying systems. Okay, so that's kind of the a little bit of a summary that, for those of you at the tutorial, we spent a little bit more time on this. But the exciting thing is that by characterizing this backwards reachable set in terms of this function J, we can now take advantage of the wealth of level set tools developed developed by Stan Osher and colleagues at UCLA, and that's what we did. So we can think, and now this is a little bit again of a stylistic interpretation of if you look at a slice through that set and you sort of turn it on its side, so now you're looking at a side view. This function here represents a side view or a slice of that function J of xt at t is equal to 0. And then when you're solving this Hamilton-Jacobi equation over time, given that initial data under the dynamics of the system, using the best control, worst disturbance, that function is going to change over time. So at time t, where t is less than 0, that slice of that function J of xt may look like this, for example. And then we look at its sub-zero level sets. And so we get this set, expanding out at this point, but frozen on this side, as we talked about. Okay, and again, just because it's important a little bit later when we talk about incorporating data-driven methods into this reachability problem, the set, if we have the property that after a certain period of time, the set doesn't grow anymore. So we say that if that's the case, the set is controlled invariant for all time, meaning that after a certain point in time, that set kind of closes off and doesn't continue to grow. Then we also have the property that any super zero level set of that function, J of xt, is also invariant, and you can use it to, say, certify safety of the problem, because if you're guaranteed to stay outside of the sub-zero level sets of J of xt, so if you stay outside of this region here, it may be easier to actually just show that you can stay outside of a super zero level set of that function. Then you're guaranteed to stay outside of the zero level set itself. Okay, so any of those may be used for safety. And then on the other hand, if the disturbance, the part of the system that we don't know or we can't characterize, this disturbance D, if more is known about that, so say you had some bounds on the disturbance, but then over time, based on data that you're receiving about the system, you learn more and more about what that disturbance looks like. Maybe you thought it was, had quite a wide worst case performance, but then over time you realize that it's much more or much less much less conservatively characterized as having a small range. Then as you learn more about the disturbance action, basically if the case is the disturbance could do less, you might actually use that information and update the disturbance action, giving you a much less conservative region in which the system is unsafe, which then gives you more region, more of the state space, more configurations which are actually safe. Okay, so we'll come back to that at the end of the talk. Okay, so here's a good time to just pause for a second, and I'm going to talk a little bit about the tools and about the computation, and then I'll integrate learning. But if there are any questions now, I don't know if it's appropriate to just pause and ask if there are any questions.
Sure, if you have any questions, you can raise your hand. Or you can use the chat if you prefer. I do not see any questions, Claire.
Okay,
So
well, let's continue. And just know that feel free to ask questions at any time, or I'll try to pause when there are natural breaks and ask if there are any questions. Okay, so as I said, this work was really the PhD. I mean, it had been work before that, but Ian Mitchell in his PhD thesis really, showed that this Hamilton-Jacobi equation and the solution to this Hamilton-Jacobi equation was exactly the characterization of the reachable set that was needed. It proved that min with zero formulation on the right-hand side of the equation, and built, once he had moved to UBC, where he's now a professor, he built a toolbox using the level set methods of Stan Osher, and developed a quite popular toolbox, which you can see the link below, for solving these problems, at least solving them in low dimension. Okay, so I'm more on that in a little bit. But here's one of the first problems we worked on. This is a particular collision avoidance control problem. We're showing results here this is X and Y. This was a lateral collision avoidance problem for two vehicles. And the details of that aren't important right now, but it's just a nice example to see that this was an actual result of computing that set. And a couple of points that I wanted to raise. So this function j of xt, again, the sub-zero level sets of this function shown in red here, that represents the unsafe region. So this is the function j of xt. The boundary of the region is defined implicitly by j of xt is equal to 0. And the magnitude of jxt at any state x at time t represents the distance. This sign distance function is the distance from x to the boundary. Again, a useful construct for control. J is negative inside and positive outside. Okay, this is just an example that we flew several years ago, and here we've got 4 quadrotors. We built these ourselves. This was several years ago now. And each quadrotor in its nominal mode is being joysticked around, flown around by one of these 4 students. And the students are trying to get the quadrotors to crash into each other. However, on each quadrotor, we're running a collision avoidance algorithm based on each quadrotor computing its reachable set with respect to the other 3 quadrotors. And on the right-hand side here, the movie's not playing. It seems like it's not working with this particular configuration. This movie is just playing the data, but it's also showing you the reachable sets at a particular point in time. And around each quadrotor are 3 sets, which represent the reachable set with respect to the other 3 aircraft in the system. So when one aircraft gets on the boundary of the reachable set of the other aircraft, that means that, if it penetrates the boundary, then there's no control law which will guarantee that those 2 aircraft stay separated. And what actually happens in this experiment is that the automation on board the aircraft, at the center that the other aircraft is on the boundary of, it starts to execute the particular safe control law So that max over U control law, that also comes out of that Hamilton-Jacobi calculation. And so the automation takes the control away from the student and executes that control law, guides the two aircraft away from each other, and then at a point when when the vehicle is not on the boundary of the set anymore, control is given back to the student. So that's a little bit of a rough transfer between automation and human, but it's illustrating the point of being able to compute and use these reachable sets in real time. Okay, and then we also wanted to say that reachability calculation is not just specific to avoiding unsafe regions. You can also use it for what we call capturing desired configurations. So again, mathematically, it's exactly the same with one important change. The desired set is now represented as a subset. So again, the initial data can be represented as a subset of the system state space. And then the backwards reachable set represents what is called in the literature the capture basin, the set of states which, for all possible disturbance actions, there's a control action which gets the system into the desired set. And the one important difference now is, just from the terminology, you might have guessed this, is that what was a max over U min over D problem in an avoid becomes a min over U max over D problem in a capture. Otherwise, the computations are the same. So one can use this framework to avoid unsafe regions, as long as those unsafe regions can be represented as a subset of the state space of the system. They can be used to achieve desired configurations, again, as long as those desired configurations can be represented as a subset of the system state space. And then you can also piece these together. So you can you can capture a desired target set, so a desired configuration, while avoiding an unsafe region. So you want to avoid the unsafe region and its back propagation for the appropriate time horizon. And I've been very interested over my career in hybrid systems, which involve switching between, systems that involve switching between a variety of continuous models. So one can also sequence these problems together. And you can compute, for example, the capture basin of a desired target set in one model, and then form a target set that's in the capture basin of that and then from a different model, compute the capture basin for that target set and kind of sequence these together. So use this in a kind of back chaining way to step through the different continuous models of a hybrid system, all the while avoiding unsafe configurations relevant for the particular model that you're using at any given time. And the nice thing is that the Hamilton, if one uses this level set formulation, the computation of this masking out one set from another set becomes very easy, because that set just becomes basically that operation is just represented as a variational inequality in the Hamilton-Jacobi computation. Okay, let me pause again and ask if there are any questions at this point. I'm going to present another example that was actually, this was in the PhD thesis of Mo Chen, who's now a professor at Simon Fraser University in Vancouver. And he's going to be speaking, I think, on Thursday this week. He's giving a talk about his more recent work in high-dimensional Hamilton-Jacobi methods. So if there are any questions, please feel free to ask or to raise your hand.
You can also use on the chat if you wish.
Okay. Okay, good. So let's continue. So So this is an example. As I said, Mo worked on this as part of his PhD thesis. There's an interest, as you've seen, there's an interest of businesses using unmanned aerial vehicles to inspect structures or to deliver packages or do things like that. And NASA became very interested in the people who work on air traffic control became very interested in thinking about how one would partition the airspace and develop kind of an air traffic control system for these UAVs, unmanned aerial vehicles. And so when in a piece of work that Mo worked on when he was a PhD student, he created this, again, it's a hybrid model showing the control of a particular UAV under a variety of control modes, according to a plausible air traffic control system for UAVs. And so, most of the time the vehicle would be in a free mode, but if it's going in flying in a busy area, the idea would be to set up ad hoc platoons of vehicles, where platoon means a number of vehicles flying along a similar altitude and flying at the same velocity, so they're easy to interpret what they're going to do. And we would have these virtual, just like we do in air traffic control, these kind of virtual highways in the sky. So these platoons of vehicles, there would be a leader and all the other vehicles would be followers or members of the platoon. This would be happening at the same altitude. So if there were, this is what NASA was quite concerned about, if there were a fault in one of the vehicles, then that faulty vehicle could, if it could affect a control action, it could descend to another altitude. So much of the action is going on at the same altitude. And so, just the control law for joining, taking a free vehicle and merging it into platoon is described by this part of the automaton where the bubbles here in this automaton represent particular control states with a continuous dynamic according to that state. And then the transitions, the arrows between bubbles represent transitions. So if merging onto a highway, it would become the leader of a platoon, or it could join a platoon as a follower. And so we studied this. We did a study for NASA in which we looked at a safety analysis. We designed this protocol, and then we looked at reachability analysis as a way to analyze the safety of this. So here are two vehicles. This is just an example where we have two vehicles, a red vehicle and a blue vehicle. And this is the highway that they'd like to merge onto. So right now they're free vehicles, and free meaning they're not part of a platoon. And from the perspective of the red vehicle, so the red vehicle is trying to get to this moving target along the highway. And the control law is basically it has to get to this particular region in which a predefined control law will snap it onto this moving target. So this becomes the region that it would like to reach. And then it detects the other vehicle. This region around that vehicle represents its avoid region. So this is the reach region, and this is the avoid region. And then as it moves, here it gets into this region. You see the avoid region is changing shape because the vehicles themselves are moving with respect to each other. And this is just a 2D projection of a 7-dimensional calculation that we did. So 7 dimensions in the relative dynamics of those two vehicles using both the XY position as well as the dynamics of the relative heading of the vehicles. Similarly, in the bottom is we see the corresponding sets for the blue vehicle, the reach set and the avoid set for that blue vehicle. So it's trying to get into the area of the reach set outside of the avoid set to get into its moving target. And here, once it's in that set, it snaps onto that moving target. And so you can see now, this is just showing that same calculation with 5 vehicles over time horizon 1, 4, 7, and 10 time units. You see this kind of organic snapping of these vehicles onto that highway. All those sets, the reach set, the avoid set, for all of these vehicles are being computed. We're just not showing them in this calculation. So what's nice here is that the reachable set calculation is being performed, and it's being used to indicate the safe switching policies. So those arrows in the hybrid automaton, when the vehicles should transition from one mode to another, from free vehicle onto joining a platoon, in order to maintain a required separation with respect to the other vehicles. And it's nice because, if you have a vehicle that's not following the rules, like an intruder, for example, this vehicle, the vehicles detect it. They see that it's not following. We're assuming here there's some way to detect that this vehicle is not following either the speed regulations or the proximity regulations. And so they compute an avoid set, and they break off. So if we look at, again, the time sequence 0.6, 2, 3, and 3.5, when those vehicles first touch, when the red vehicle moves in such a way that the other vehicles first touch the boundary of the reachable set, they automatically break off from the highway to avoid that set, and then they return afterwards. So it's kind of like the development of a series of a protocol which involves switching from one control mode to the other based on the computation and the use of these reachable sets in real time. Okay, so real time brings me to the next piece of this talk. We've talked about the Hamilton-Jacobi formulation. We've talked about the level set computation of that, and we've given a couple of examples to motivate it. The key problem, and I think really the guiding reason for this workshop that we're having is the problem in high dimensions. So computing the reachable set, in general, it requires us to grid up the state space. So the dimension of the continuous state space is always the problem. The higher the dimension, the higher the inability of us to compute this set in real time. So those computations that I showed were 7 dimensions in the example that we just computed, but we were able to get some savings. So typically about a 4 or 5 dimensional problem in terms of the continuous state space is something that we can do without any manipulations or other methods. But going beyond that, either the discretization of the grid has to be very, very coarse, basically the number of grid points per dimension, or you need some other kind of approximation method to do this. And so that's really what we've been working on, and not just us, others. So for example, the problem that I just showed, imposing practical constraints. I mean, the reason for using highways in the sky is that you're not needing to compute your constraints with respect to every other vehicle, just the vehicle in front and the vehicle behind, or maybe just the vehicle in front if you follow the kind of protocol. So that means that the dimensionality of the problem, which is increased as you increase the number of vehicles, can stay fairly small. And you can use these, for example, 2 vehicle relative models in these computations of, even when there are many vehicles, as long as vehicles are following the protocols. Which you could see in the intruder, the vehicles had to not only, control themselves with respect to the vehicle in front, but they had to control themselves with respect to the intruder. Okay, so other types of methods that people have used, and I've referenced here researchers who've worked on these areas. I haven't given dates, I've just given names, and this is not a complete list. But it's a list of people that I've been influenced by in terms of, people that have worked on really neat solutions in different categories. So what I tried to do was kind of categorize different methodologies that people have used and put them here with the appropriate researchers' names next to them. And I'm missing people, and I apologize for that. So approximations. Now, approximations could mean approximating the dynamics of the system, approximating the set structure. So maybe not using level set methods, but using, for example, polyhedral or ellipsoidal approximations, which can save, in some cases can give some computational savings. And so you see some of these, like, for example, the use of linear, piecewise, and multi-affine systems. Linear dynamics are easier to treat and easier to compute with in general than our nonlinear systems. So looking at linear approximations of dynamics has been, or even piecewise linear, has been something that we and others have taken into account. Approximating the set structure, like ellipsoidal and polyhedral sets. There's been quite a bit of work there. Looking at polynomial dynamics and savings that can come out by using by looking at the semi-algebraic structure of those polynomial systems, or barrier certificates like control-Lyapunov functions. There's been quite a bit of exciting work done there, which I feel kind of stems from Pablo Perillo's PhD thesis on using sum of squares for polynomial systems and constructing barrier certificates to use as Hamilton-Jacobi-like functions. Other methods that I'm going to spend a few minutes now talking about involve decoupling disturbances and decompositions. So being able to break down a problem into lower dimensional structures. There are others looking at mathematical structure. If you know the system's monotone, or if you can simplify the system using linear temporal logic, then you can have some gains. And people have been working both in the control and computer science verification community, as well as in the mathematics and applied mathematics communities. Okay, so let's go to one of these. This is a topic that that Mo Chen worked on, and I think he might mention it in his Thursday talk, this idea of system decomposition. So here is, and not just Mo Chen, but Sylvia Herbert as well. So Sylvia is a PhD student graduating from my group this year, and she's going to be giving a talk on Friday, I believe, in this workshop. Okay, so self-contained subsystems. So the idea is, suppose you have a system, and let's just suppose there's no disturbance for now. Actually, we think there are some cases with disturbances that we can apply this technique to, but for now we have only worked on mainly we've only worked on cases where the control system has an input but no disturbance. And suppose those subsystems are self-contained. What that means is that, in the subsystem, you have all of the variables that you need to evolve the state variables of interest. So let's look at an example below. Now, this is a 3D system. You don't really need to do anything. We could do this one in real time, but it was a good test of the technique just to visualize and show what's going on. So suppose you had this Dubin's car system where state variables x, y, and heading theta represent the state, and then these are the dynamics, or I guess kinematics, describing the motion of the car. So you could go ahead and, as I said, just compute the 3D reachable set directly. Or you could break it down into two-dimensional subsystems. So one subsystem involves x and theta. The other involves y and theta. And you can see, first of all, that there's an overlap in variables. Both subsystems contain the theta dot variable. And that's because in order for the subsystems to be self-contained, we need theta. We need access to theta to compute this state variable x. So, every variable that you need to compute the evolution of x and theta are given here, is given here, and similarly for the evolution of y and theta. All right, so that's the key thing, that you're allowed to repeat variables across subsystems. So now instead of having one 3D system, we have two-dimensional subsystems. We can compute the reachable set of each subsystem separately. So that's, in this case, again, it's not that significant because you've gone from 3 dimensions to 2 dimensions. But in general, if you could do this as a general tool, which you can't yet, but there are many cases which do work out, then you could get some significant computational savings by essentially removing some of the state variables in your computations. And then the idea would be, if you could do these two computations, can you piece them together to somehow get back the full 3D reachable set without actually computing it? And so this is the example that we have where the idea is to try to avoid this, this region here. It's a square obstacle in the position space, so in X and Y. And we've backpropagated over the theta. It doesn't matter what angle you want to avoid it at. You basically want to make sure that you avoid that set. And so here, the set that you're trying to avoid can be represented in the two individual subspaces. You can project that set down, and more importantly, its back projection actually represents the set itself. So the set that we want to avoid can be represented as the back projection of corresponding sets in the individual subsets of the state variables. Now, in general, if you want to avoid a set, you don't need the set itself to be represented that way. You just need an over-approximation of the set itself. So, for example, if you were trying to avoid these disks that we were using earlier, you could come up with this rectangular prism over-approximation of a circular cylinder. Okay, so we take the intersection of the back projections. And now with that set structure, we go ahead and we compute the reachable sets in each of the projections, in the x theta and the y theta, and that's the computation done here. And so what we're doing is we're just doing two-dimensional Hamilton-Jacobi computations, but we're maintaining the back projection here just for visualization so that you can see that the actual set is actually a very good approximation. In this case, it's an exact computation of the actual reachable set. So this is what we get through decomposition, and the blue is what we get through direct computation. But the complexity has decreased because we've decreased the dimension of the problem. Okay, and we worked on a number of examples here. So we've gone from a 6D quadrotor system to, and not just using, in this case, we weren't using just self-contained subsystems and decomposition. We also employed the use of the fact that there's an integrator in the system, and so we can get some computational savings there. I'm not going to talk about that here, but overall, in this problem, we only had to compute two-dimensional subsystems to be able to get the actual 6D full system. And here is a visualization of that. So again, we're visualizing the set in its projections. So it's done, the dimensions are relative. So the X and Y positions here, then the heading with respect to X. And then when we look at slices, we're basically looking at the velocity. So it's taking slices over the velocity. Okay, so here's just sort of a visualization. The angle of rotation is described along the phi axis. And sorry, let's just go back. And so we can basically compute that set and then, visualize that set in terms of its projections. We've also computed, and I showed this when we were giving the tutorial talk, this reachable set for a 10-dimensional near hover quadrotor, which the dynamics are shown here. And this can be broken down into two 4D subsystems and a 2D subsystem. Actually, this is what we would call trivially decomposable, because you don't need any overlap of state variables, and that and those, because of this integrator trick, can be broken down into two 3D subsystems and a 1D subsystem. And so this 10D set, again, the challenge here is visualization. We're always trying to visualize meaningful projections. Sometimes you don't even need to reconstruct the set with the subsets that you've computed in the lower dimensional spaces. It's often enough. Okay, so this, again, the co-authors of this work are Mo Chen and Sylvia Herbert, who will be talking in more detail with more examples about this and its extensions later this week in their talks. Well, at least Sylvia will. I think Mo might talk about it a little bit too. I'm going to skip this next bit because I spent some time, and the tutorial was recorded, about using offline computation a couple of weeks ago in our Hamilton-Jacobi tutorials for this whole long program. And also I'm going to skip it because Sylvia on Friday will be spending more time going into more detail than I presented either at the tutorial or I could present today. So the idea here is to use offline computation, so it doesn't really matter how long it takes to compute, but to compute offline and store that and then use it in real time for robotic path planning. So I'm going to just jump out of that and skip the next few slides. So this was example 3 of Fast Track to go on to learning. So Sylvia is going to present this on Friday, to go and spend the last 5 minutes of today's talk talking about learning dynamic behavior safely. Okay, but before I launch into this last 5 minutes, and we'll have questions after, but are there any questions about what I've presented so far? Okay, so let's go into the learning dynamic behavior safely. I alluded to this at the beginning of the talk, but the idea here is this computation is, this Hamilton-Jacobi computation is based on assuming worst case action about a disturbance. So we assume that some effects, like actions of other players in the system, other aircraft, wind for the aircraft problems, you know, the behavior of things in the environment that aren't well characterized, that we put some bound on those, and then we basically compute this reachable set to protect against the worst case action of the disturbance. But in real life, you know, if we're somebody who's learning how to drive, we're very conservative typically when we start. We don't know what other, you know, merging onto a highway is a challenging thing. We don't know what other vehicles are going to do, but over time we learn the flow of the traffic, and we learned about, you know, behaviors of different drivers, and we get better adept at controlling and not being so conservative. And that was the idea here, is to try to mimic that process using machine learning. So we started by saying, what if we had computed a reachable set? In this problem, we have a quadrotor. It's doing something very simple. It's just going up and down, up and down. It's trying to follow a step trajectory in the vertical dimension, just going up and down, up and down. But we compute that using a model, and then we take the vehicle's model away from it. So it has to learn a model of itself and a control law to try to track that trajectory, yet still maintain safety. So it knows about its safe reachable set, its envelope for not hitting the ceiling and the floor in this case, but it doesn't know its own model, and it has to learn that. So here it drops down to the bottom. It doesn't crash because the safe controller steps in. Here it's speeded up a little bit. And then after a little bit of time, it starts to do a pretty good job of tracking this desired trajectory, this blue dashed line. The red is where the safe controller is stepping in, so it doesn't violate the safe envelope near the floor. Okay, so this is really a little bit artificial, because who computes things and then takes the model away? That was more of an academic exercise. But the idea was to use this to try to mimic that driving process that I talked about. So the idea, now we'll kind of close the loop back to the beginning of the talk, is to maintain this reachability, this reachable set, as kind of I sometimes describe it as like bookkeeping. You've got your model, and you're always kind of updating your disturbance model and updating reachable sets in real time based on that disturbance model. So you start out, for example, with your nominal smallest candidate unsafe set, and you start to get measurements over time, which may violate that disturbance, your assumption about the disturbance. If it does, grow it to a super zero level set. We know that we can maintain safety for that with the old model. So as the disturbance grows, if we use the level set from the Hamilton-Jacobi calculation that corresponds to the disturbance that we're measuring at that instant, then we can maintain safety. And over time, the question of how to update these sets reliably so that, you're shrinking it in a way that's reliable is interesting. But over time, you might expect that as you learn more about the disturbances in the system, you actually become less conservative. So the last experiment that I'm going to show, and we'll finish up with this one, is this experiment where we sequentially ran two experiments here, and you'll see them superimposed on top of each other. This was done by Jaime Fizak and Kene Akamatalu. They followed the same experiment of asking the quadrotor to go up and down in a room and not violate safety, yet there's an unknown to the quadrotor and unknown to the computation of the reachable set. There is actually a wind disturbance that's turned on halfway through the experiment, which produces kind of a big disturbance in the bottom part of the room from this fan that was not accounted for in the model. And so what this experiment is doing is trying to mimic, or trying to, not mimic, but trying to try out this safe learning mechanism that I described in the previous view graph, where as the vehicle gets close to this now area where there's a disturbance that's unknown, it shrinks back its reachable set. So the safe region is now inside this envelope, and it goes back to that particular part of the envelope where the disturbance that it's measuring will still cause the vehicle to stay safe. The shaded out vehicle is the one that is not doing this online update. Okay, so the vehicle is updated that envelope in real time based on the safe level set of that Hamilton-Jacobi equation. Okay, so we'll just finish this part by saying we talked about learning while staying safe. We talked about safety from reachability analysis, a little bit about the simplicity of a hybrid system representation using a multitude of different models for different configurations of the system and switching between them. And then we ended in the last few minutes talking about the ability to learn from new information. So how do you update? These are questions we're working on now. How do you update these? How do you decide when it's safe to expand your safe region of the reachable set? That is context specific, it's application specific, but how do we do that? This is in the learning community, they would use the term learning rate, but how do we apply that to safety critical systems? And how do we model unstructured environments? So how do we take that kind of computation and apply it to scenarios where you're learning much more than just a disturbance that's affecting the right-hand side of your differential equation? You're learning about the environment itself. You're learning about people interacting with the system. And a PhD student, Samuel Bansal, who's in my group, who's graduating this year, has worked on this for his PhD thesis in the context of Hamilton-Jacobi methods, and he's giving a talk also this Friday. So later this week, we'll go into some detail on these different methodologies. And then finally, we're working on the concept of risk-sensitive reachability, introducing a stochastic framework, using information, maybe a stochastic distribution about the noise. So if you have that information, why not use it? And that's been the work of Margaret Chapman, also a PhD student in my group who's graduating this year. Okay, so with that, I'd like to conclude the talk. I'd like to thank a number of students and former students who have been working on this. And again, you'll hear from Mo later this week, and you'll hear from Sylvia later this week, and also Samuel later this week. And I think, is Ian Mitchell also speaking this week, perhaps? I think, he's been involved in this as well. So, and a number of these folks I know are participating in this workshop. So just shouting out to them to thank them for all their great work in this, and also to the funding agencies. So it's been great to have the support of these agencies over the years in this work. So with that, I'd like to conclude, and I think we have a few minutes to ask questions that people might have.
Thank you very much, Claire. Are there any questions? Yes, Jan, 1 second. You can go.
Hi, Claire. Thanks for the advertisement. That code is getting a bit old.
Hi, Ian.
So I wanted to ask, you're doing some of these computations, and some of them are designed to be run online, some of them are designed to be run offline. How heavy duty is this compute that you're doing? Is this something that you might at some point port onto a embedded processor that could actually be on a quadrotor or in a car? Or are they really dependent on sort of high-end desktop or GPUs?
Yeah, that's a really great question. Definitely the pre-computation was meant to address that in a very near-term way. So do the pre-computation and then use that structure online, but it's not doing any of the computation online. But the being able, I do think that whereas right now we're not running any of these computations in embedded processors, we're using high-end desktops, and we're even in the cases where we are I'm going to say that with one qualification. Even in the cases where we're computing these in real time, we're going back to desktops and asking them to do the computation in real time. With the exception of one project that we've been working on recently, which Samuel will talk about on this Friday, where we took advantage of the fact that, so he's working on navigating robots in unknown environments and making some assumptions about the environment, namely that they're static, that if you see things and you perceive obstacles, those obstacles aren't going to move or change. At least for now, that's the assumption that he made. Then the level set function, which is representing the free space and the obstacle space, is as you're moving through the environment, that what you're learning about the environment is only it's not like something that you just learned is going to change at a future time. So in those cases, he and another student in my group, Andrea Baichi, who's also she's here. They have been trying to take advantage of as you move through the environment, what you're going to be learning about new obstacles are typically they're going to affect the environment, or they're going to affect your representation of the environment locally. So those local computations, just looking at the edges of obstacles and seeing how they change over time as you're moving, that update is being done in real time on the actual processor on the robot. So that's something, because that we're making the assumption by all of these assumptions about the environment that the only changes in the level set function are happening local to the zero boundary in certain regions. We can do that in real time on board embedded processors. But in general, that's a special case right now. And I think what you're bringing up is where I think we want to be. We'd like to be able to develop embedded versions of these that can run in real time on robots that are out there and provide safety filters. So it's a great question, and I think it's where we want to be in general.
Okay, thanks. I do have another question, Jerome, but I'll leave it to you whether there's time.
Let's go.
So my other question, Claire, was the techniques that you used to solve these were based on level set techniques and finite difference approximations, which are 15, 20 years old now. This morning we had heard about algorithms using machine learning to solve these high-dimensional PDEs from Key and from Weinan. And I'm wondering, you're solving a very specific problem, which is solving for these reachable set boundaries. Could the numerical methods that we heard about this morning be applied, or are some of the assumptions going to be that were in the techniques this morning? Are they going to be broken?
I don't know the answer to that, Ian. I think that this I think that this deserves more. I mean, we need to look and see whether or not we can apply these at the tutorial sessions, or maybe day one. Jerome presented some, and Adam presented some really interesting work along some of these lines too. And I think that we might be able to use these tools. I just don't, honestly, I don't know yet, because we haven't looked into it in any depth yet.
Okay, thanks. I don't know if she has anything to add.
Are there any other questions?
Or perhaps comments from the speakers this morning to, as Ian said, to ask if some of these learning tools might be used to significantly update the numerical methods that are performed for these Hamilton-Jacobi equations.
Yes, so Wei has a question.
Hi, Clara. Yes, very nice talk, and I'm glad that Ian asked that question. So I have just one comment. I mean, I think this is, to me, the machine learning approach is very new. I think we9 also just started to work on that a few years ago. I agree with Clara that I think it's worth to look into it. Just one, comment, very premature. Okay, we had a simulation, because for this type of HJ equation, it's a characteristic. It's kind of solving ODEs. We did something like we tried to learn the propagation of a distribution function in Lewis equation. So then we propagate the characteristic was relatively straightforward. We tried that. There one example which was relatively successful. Another one was not so much successful. It's really depend on I think it's related to how the dynamics push the level curve out, I guess. So anyway, I think it's a very interesting question. We just did a very shallow preliminary study for a couple of cases, but definitely we should talk about that. Yeah.
Yeah, I think it's a great question, and thanks, Ian, for bringing that up. It's something that I've been interested in since John Ligaros several years ago. Also, but it was before. Actually, it was several years ago now, so I can't remember the year. But he had published a paper in at this topic, trying to use learning methods to compute again the characteristics of Hamilton-Jacobi equations. And I think, at that time it was a little early, and I think this revisiting now, like you're doing, is exactly the right thing to do, and it's very exciting.
Okay, are there any other questions or comments? Okay. Claire, thank you very much for your talk.
Thank you.
So this concludes the afternoon session.